Hello, my name is Paul Mellon. Welcome to my demonstration video for MAE 535. Today we're going to look at a Hall effect sensor. A Hall effect sensor is a sensor that detects a magnetic field. But before we get into the sensor in more detail, let's look at the physics that are behind how this sensor works. The Lorentz law states that a charge Q moving at a velocity v, an electric field E, and in a field of magnetic flux density B causes a force F on the charged particle according to this relationship. This shows that there is a force on a charged particle from both an electric field and a magnetic field. If there is an electric field but no magnetic field, the second term reduces to zero and the charge is only affected by the electric field. However, when there is a magnetic field, the cross product of the velocity and the magnetic flux density shows that it will induce an additional force that is perpendicular to both the velocity and the magnetic flux. This is the typical layout of a Hall effect sensor. It is constructed of a thin plate of semiconductor material and a closed-loop DC circuit. Without the magnet, current flows through the sensor based on the electric field produced by the DC power supply. A magnet introduced near the semiconductor interrupts the typical flow of current in the sensor due to the Lorentz force. The magnetic field induces a force on the charged particle that is perpendicular to the current flow and the magnetic field. This causes charged particles to collect at the ends of the plate, which creates a difference in voltage between the two ends of the plate. This voltage is called the Hall voltage. A change in Hall voltage indicates there is an applied magnetic field. These sensors are typically used to operate brushless DC motors, sensing when to turn the electric field on and off to keep the rotor spinning. They are also used to sense the speed at which a motor or other rotating shaft turns, but they are also used to sense when an object is near to another object, such as to detect when a flip phone's lid is closed or when a smartphone has been placed in its carrier. This is my CNC milling machine. Depending on the type of material being milled, different cutting speeds are recommended. However, if you look at the motor speed control knob that adjusts the rotational velocity of the cutting tool, you will see that there is no indication of the revolutions per minute. The only way is to guess at the motor speed based on the relative position of the knob and the whine of the motor. This project uses a Hall effect sensor to measure the speed of the cutting tool. The output of the sensor is read by a Raspberry Pi single board computer. Code was written in C to display the output on any computer, smartphone, or tablet logged into the Raspberry Pi. First, the CNC machine was used to cut out some discs of plexiglass. These discs were then milled in such a way that magnets could be placed in the disc and the disc could be placed on the shaft of the cutting tool. Next, another small piece of plexiglass was milled to hold the sensor just above the magnets as they rotate around the shaft. The sensor used for this project was a latch-type sensor. This picture from the manufacturer's datasheet shows that the sensor turns on in the presence of a magnetic north pole and turns off in the presence of a magnetic south pole. This way, two magnets can be used 180 degrees from each other with opposite polarities. As the shaft rotates around, one magnet will latch the sensor high and the next magnet will latch the sensor low. This will produce a nice square wave from which the frequency can be detected. This shows the Hall effect sensor in operation. This is the signal generated by the sensor as depicted by an attached oscilloscope. In order to determine the frequency in code, I use the discrete Fourier transform, or DFT. The DFT of a square wave produces multiple frequencies in the frequency domain because it is constructed of many signals of different frequency and magnitude. In order to determine the frequency of the square wave, the largest magnitude corresponds with the carrier wave or base frequency. So I sampled the signal every 5 milliseconds, computed the transform, and found the peak magnitude to determine the frequency. This method was very stable and was accurate to about 1 Hz when measured with the frequency on the oscilloscope. This shows the output from the Hall effect sensor and the transformation into the frequency domain. Well, there's a lot more I'd like to show you about this project, but we're out of time. Thank you so much for watching my video.